Right, so the first thing that you're going to need to do with this question, and we'll call it part A. So part A, I'll just change my thickness to there. So part A is going to require you to always find the velocity. Alright, so we're going to find the velocity using part A. Alright, please work. So that's the first thing that we need to do, is find the velocity of our particular electron. So using our electron gun, okay? So the electron gun scenario. Now, sometimes they'll give you the velocity, which means that you don't have to do this part. But if they don't, then you need to do this. So what was the formula we used the other day when we were doing this? What was the formula we used? What did it gain? Gained energy, right? And the form of energy that it did gain was work, wasn't it? Okay, and we know work's equal to Q delta V. Right, and then we know that that work is equal to the kinetic energy that it gains. So that's equal to a half mv squared. And we could rearrange that formula, right, to do what? We could rearrange that formula to work out the velocity.
Yeah.
So velocity is equal to the root 2 of 2 ke all over the mass. Okay, and that will give you your velocity of your particle. Alright, so we have to work out this first of all. So that was equal to the charge, and it's electron, 1.6 by 10 to the minus 19. And for this one here, we've got 1,000 volts that's accelerating that. So your energy could be called 1,000 electron volts, couldn't it? And that 1,000 electron volts is equal to 1.6 by 10 to the minus 16 joules. Okay, you can work that out in your calculator if you want to, but that's what it's going to be equal to. Alright, so we obviously, when we're working our velocity, you have to be in SI units, so we have to be working in joules, don't we? Alright, so if we work out our velocity is equal to the square root of 2 times that value, 1.6 by 10 to the minus 16. And that's all over the mass. Now, it's a mass of electron that we're actually accelerating, so that will be, when we look at that, the mass of the electron is 9.11 by 10 to the minus 31. Alright? So that will give you the information that we need to work out the velocity. So if we go to our calculator, bring our calculator up, and we can do that on our calculator in terms of one question. So one thing. So again, as we said before, let's do the top line. That's 2 times by 1.6 to the exponent minus 16. And then we're going to divide that by our bottom line, which is going to be, what was it? Just the mass of a proton. 9.11 to the minus 31. Okay, and then that will give us our particular speed. So that's, what is it? 13. So that's 1.87 by 10 to the minus, by 10 to the 7. Okay, so that's a pretty fast speed. So that's equal to 1.87 by 10 to the 7 meters per second. Alright, so that is our velocity. So you don't really, once you've done a few of these questions, you'll get used to the concept of what you've got to do there, working out your velocity. Alone, just bear with us. I mean, I'm not expecting you to know any of this, but you do. Awesome. Okay, great stuff. So back to our diagram. So what we're looking at here is we're looking at this part of the diagram. So we've now worked out our velocity, the speed that our velocity goes through that part of the diagram. So part A is really just working out that part there. Alright? You okay with that? Alright, so the next part of what we're going to do here is work out the electric field strength inside this particular part there. Alright, so that's always something you need to do. So part B is to work out the electric field strength. So sometimes it will ask you to work that out, sometimes it won't ask you to work that out, but it's one of those things that you do need to do. Alright, so the electric field strength, E is equal to the potential difference, the voltage, all over the distance, isn't it? Alright, so in this particular case, what's the other formula we've got for electric field strength? Force over the charge, that's newtons per coulomb, isn't it? Okay, so this one here is volts per metre, is the units that we're going to use for that, for electric field strength. So what is the potential difference that we've got here? Well, it's over 1 centimetre and it's applying 50 volts in that particular thing. So our electric field strength is going to be 50 divided by 1, which is going to be, oh actually not 1, it's 0.01. So that's going to be 5,000 volts per metre. The units are volts, and then obviously we're using metres for distance, aren't we? So that's 5,000 volts per metre. That our electric field strength is there. Right. The other thing, so that's what we've got there. We need to also work out what our part C. We need to work out the acceleration. Alright, so to work out the acceleration, we're looking at what's the acceleration due to the electric field. Alright, so it's a bit like the gravitational field, as I tried to explain the other day. Imagine the big plate here and the big plate there, and we're throwing our electron through there. It's going to go parabolic motion, isn't it? Alright, so rather than remembering the formula, but you do have a formula sheet, so it's got some of the stuff on it. We know that force is equal to mass times by acceleration. So therefore, acceleration equals force over the mass. Now we know that the force is equal to what? What's electric force? We do know that E is equal to... So? No. There's on your formula sheet, get your formula sheet out. What do we know about electric field strength? Electric field strength is a relationship with force on there. You need to be able to identify these things so you can derive them. I'll beat you. Alright, so these are the formulas that we have up under here. We know that E is equal to F over Q. Alright, we also know that E is also the potential difference over D. Alright, electric field strength. So all of these formulas here are the ones that we're using. So if we go back to our formula here, we know that E is equal to F over Q. So therefore that means that that's equal to, F's going to be equal to EQ over M. So that's going to be a formula to work out your acceleration, isn't it? Right, so in this particular, EQ over M. Q is charge. Right, so sometimes, as I said the other day, is we won't use Q, we'll use the letter E, little e, which represents a charge of an electron. Alright, so that's what you'll see sometimes. So if we want to work out acceleration, A is equal to E, which we already know, which is what? 5,000. We know that the charge is 1.6 by 10 to the minus 19 coulombs. And then the mass of electron is 9.11 by 10 to the minus 31. So again, you can go to your calculator, you can do that calculation. Can someone do that please for me and get an answer? Now I'm looking for something like 10 to the 12, 10 to the 10 metres per second. Right, you've got your calculators out? So it's
8.78 times 10 to the 14.
so 8.78. 8.78 by 10 to the 14 metres per second squared. It's an acceleration due to the electric field. Alright? It's not a huge voltage, but it's not a very big gap. Alright, it's actually quite close to the gap that we're looking at there. Alright, so that's part C, is to go through the acceleration. So once we've got that, what we want to know is how long it's going to take, how long it's going to be in the field. Alright, so part D will be the time. The time it's in between the plates. Between the plates. So what that's going to be useful to do is, what do we know about our most basic formula for distance and speed and velocity and all that sort of stuff? Velocity is equal to the distance travelled over the time, isn't it? Yeah. Okay, so that's our most basic thing. So velocity is equal to the distance, displacement over the time. So therefore, our time is going to be equal to our displacement over our velocity. In other words, that's really the length of the plates. So how long are the plates? Do you remember? 3 centimetres. So that's going to be 0.03, and the velocity is the velocity it enters, and that was, if we go back to our thing, 1.87 by 10 to the 7. So that's 1.87 by 10 to the 7. Put that into your calculator, and that will give us our time that it's going to be in between the plates. So the time's equal to, calculator people, 1.6 by 10 to the negative 9 seconds. You need to get a feel for the sort of answers that you're going to get. So you know your acceleration's about 10 to the 10 to 10 to the 14. This one's always going to be about 10 to the minus 9. It's only going to be a very short period of time. Right, so next thing I need to do is I need to work out how much it's going to be deflected.
So we have to do this process for every question?
No, there will be parts of this that you have to do. I'm going through a complete full question, everything that you could be asked to do in a question. Alright? Now, as I said before, is a question won't have you doing all of these parts, but will get you to do some of these parts. Yeah. Alright? So this is like a cheat sheet sort of question for you. Alright, so part E, and I'll save this document up on Daymap for you as well. So this is actually working out the vertical displacement. Alright, so the formula we're going to use for this is SV is equal to VVT plus a half of AVT squared. And we've already done a whole heap of work in projectile motion, so this is the same thing. Now, our vertical velocity when it came through was equal to 0. It came in horizontally. So T, so that's going to go out. You're not having to worry about that. We've just worked out what our AV is. Right, our AV was 8.78 by 10 to the 14. So that's 8.78 by 10 to the 14. I'm going to times that by our time, which is 1.6 by 10 to the minus 9, and we've got to square that. And that will tell us how much our vertical displacement is. Right, so you put that straight into the calculator like that, and you get an answer for our SV. Right, shout out an answer when you get one. Negative 31. That's a mistake there. What did you get, Alex?
1.1 times 10 to the negative 3, negative 2.
Negative 3?
Negative 2.
Negative 2? Negative 3 metres.
Yeah.
So that's equal to 0.001, let's say 1, right, metres. So it's actually going to be not even a centimetre it gets deflected, isn't it? It's 0.1 of a centimetre, like 1.1 millimetres is how much it's going to be deflected, right, from that thing. So if we were looking at this going through our particular thing, it's going to go through here. It's probably going to get deflected about this much. It's going to go through right? It's going to not be deflected very much at all. So it's actually going to exit that particular plate quite nicely, isn't it? All right. So coming back to our last bit, so that means that it's going to get through the plates. It's actually going to exit, right? And it's not going to hit the side plate. That's what we're looking to see. Some of the questions will ask you, does it hit the side plate? Does it exit the thing? So therefore exits the plates. What do you think the last thing we would have to do in this question? Part F. What did we do in the last part of projectile motion? We know how much it's been deflected up and down. Right, so find the final or the exit velocity. Okay, because remember it's picking up some vertical velocity now, not just what its horizontal velocity is. So if you think about this, it's coming like this over here. Its velocity is 1 point, what was it? 1 point, no it wasn't. It was 8.7, wasn't it? 1.87 by 10 to the 7 metres per second. That's its V horizontal. And then it picks up a small V vertical, doesn't it? Agree?
Yep.
And so therefore its exit velocity is going to be the one where it's got that direction going that way. So that's its final velocity. And so you'd have to work out its angle as well. Do you remember the formula we used to work out the velocity here? The velocity V is equal to its initial velocity plus A V times T. So in this case that's equal to 0 because it had no initial vertical velocity. It was coming in totally horizontal. Now, you know the other day when I spoke about coming in at an angle, it would have an initial vertical velocity in that case. Right? But most of the time you'll find this will be 0. Our acceleration is what? Work that out. It's 10 to the 14, isn't it?
Yeah, 8.78.
8.78 by 10 to the 14. Our time is 1.6 by 10 to the minus 9. And so therefore you can work out what its velocity is going to be by just timesing those things there. Alright, now obviously I didn't look to see which one's a positive plate or the negative plate. I'm assuming here that that's the positive plate up that way. Whether that's true or not. What was? Wow, how good's that? I was lucky. Alright? You would need to make sure you get that right, because that shows a concept of whether you know it's going up or down. Alright, it's actually going to go towards a positive plate, isn't it? Alright, so in terms of this next bit, so you've got an answer for me here? Answer?
1.4 times 10 to the 11.
To the what?
11.
That can't be right, can it?
It's not supposed to do a 6.
10 to the 6
Yeah.
metres per second. So 1.4?
Yeah.
So did you have negative 9 there?
Yeah.
What? 8.78, 10 to the 14? Just make sure his calculator works properly.
Oh yeah, it is to the 9.
To the 9?
Negative 9.
Negative 9, yeah.
You were negative 4.
Yeah, well, it's negative 9.
Not really.
Yeah. Alright, you can't read my writing. I can't read my writing, so good luck. Over here, so we know that's 1.4 by 10 to the 6, and we got to square that. So when you do that calculation, someone can do that. To work out the angle, theta, that's going to be, remember, tan to the minus 1 of 1.4 by 10 to the 6 all over 1.87 by 10 to the 7. Alright, so someone can work out the angle, someone can work out the actual velocity just using Pythag. So when you've got an answer, shout it out. Angle be nearest degree would be probably, it might only be like a smidge of a degree. It's not going to be deflected very much, is it? If it's 1 millimetre over 3 centimetres, the angle cannot be very big at all. So if you get a decimal place for your angle, I would be thinking you might get it right. Right, who's got an answer for the distance, the speed?
1.87 times 10 to the 7.
By 10 to the 7.
Yeah.
Okay. Meters per second. What does that really mean? Could that be possible? Yeah, it just means that the vertical component is like minuscule compared to the horizontal velocity. Right? So if you're looking at the process that I've done there is really important. So what it would mean is maybe I needed to go to 3 decimal places or something like that to actually get some variation. But I'm okay with that. You've shown the formula, so I give you a mark for doing this bit here, yeah, and then writing your answer down. Alright? Get a mark for putting, I'll probably only going to give you 1 mark for doing that, but if I can see that you've done the right process, then that's good. Got an angle? It's doing your head in? 4.2. 4.2. 4.3. Did you round up anything?
Yeah, because it was 4.28.
Yeah, 4.3. Okay, so 4.3 degrees. So you should make a statement something like the electron exits the plates with a velocity of 1.87 by 10 to the 7 meters per second at 4.3 degrees above the horizontal. So that's the sort of thing that you do. Alright, so that is a complete question. So as I said before to you, you could get asked to do every part of that in a question. Chances are not, okay? But you could get certainly asked to do some parts of that question. Alright, so you need to be aware of that. It's a bit like, you know, when we did projectile motion, some of the questions didn't ask you to find the vertical and horizontal components of velocity, but you need to do that anyway. Right, so when you start doing that part, that would be the example of working out the electric field strength. Sometimes it won't ask you to do that, but you can't do these questions without it, because you need that electric field strength to find the acceleration. So sometimes I'll say, oh, and it enters a particular plate which has an electric field strength of this. Right, so I actually tell you that so you don't have to calculate that part. So when I'm doing a question, I'm in your test probably going to ask you two of these. One will be maybe electron gun and parts of. The other one will be doing other parts of it. So if you stuffed up the first part of this question, it's not going to impact on the whole question. Does that make sense? So I'm essentially probably going to ask you two of these questions, right, on this, that will go through all the parts of that particular stuff. That's what you're going to expect from me in the exam, in the test. In the exam, don't know what you're going to get. You're going to get probably most of those parts in one question. Alright? And this is sort of like a question in the second part of the exam, where it's a lengthy question. It's a bit bigger question. Right? So that's what you'll expect to see there.